The Books Podcast, presented by Tim Hague.
Welcome to the Books Podcast. I'm Tim Hague. Now, we like to think we have a fair range of interest at Books Podcast, and indeed, we've covered fiction, biography, politics, economics, history, science. Just go have a look. Please subscribe now on your favourite podcast player to hear the back catalogue of fascinating interviews, and please do let us know what you think. Well, I mentioned science, and sometimes hubris overtakes us, and we invite an actual scientist onto the show. Marcus Chown is an award-winning science writer and was formerly, I think, a radio astronomer, which is to say that he knows a little bit about the amazing cosmic objects known as black holes.
Not only are black holes not black, they don't appear like holes sucking in material, but very often we see jets of material coming out of their poles. Supermassive black holes are very tiny. I mean, imagine a bacterium compared to London. But we find that they've left an indelible print on the stars.
I ask you, gentlemen of the jury, is this the kind of book you'd like your wives and servants to read?
Marcus, thank you for joining us on Books Podcast.
Oh, thank you for having me.
I suppose we'd better start off with what is a black hole, because there's a sort of popular conception, and it's a lot less interesting than what they really are. Most people think, oh, it's a black hole, it's the event horizon, and then light can't get out, and it's somehow inert and dark, but that's not actually what we're talking about at all, is it?
Yeah, so basically a black hole is a region of space where gravity is so strong that nothing, not even light, can escape. Or to put it another way, it's a place where space-time is warped into a kind of bottomless well from which light cannot climb out. And you're absolutely right. In the first part of the 20th century, people thought these things would be completely black, and therefore they didn't bother to look for them. But actually what they forgot is that every star tends to have a companion. I mean, our sun is quite unusual in being a solitary star. Most stars are binary stars. So when you have you have a black hole with a companion, then there's the possibility of material being sucked off onto the black hole, being heated to millions of degrees, and glowing brightly. And black holes are some of the most luminous objects in the universe.
We will have to explore that in a minute, but I'm going to take you back. You said the beginning of the century. They weren't even thought to be a thing until 1915. And one of the joys of the books is that you tell the story of the people and the devices and the theories that led to the history of black holes. And we have to start off with Schwarzschild, because he's amazing. And I've heard the term, Schwarzschild radius and things like that often, but it hadn't occurred to me that it was probably an actual person. And he's a really interesting fellow.
Very interesting, and he had a very tragic life. But he was actually the director of the Berlin Observatory on the outbreak of the First World War in 1914. And he joined the German army, even though he was 40. He didn't need to join up because he was Jewish and anti-Semitism was on the rise in Germany. And so he wanted to show he could be a patriotic German. He ended up running a weather station in Belgium, calculating shell trajectories, and he ended up on the Alsace front, the only mountainous bit of the Western Front. And incredibly, in November 1915, on leave, he went to Berlin and he attended one of the 4 lectures that Einstein gave. Einstein gave 4 weekly lectures in which he presented his new theory of gravity, which supplanted Newton's theory of gravity. And the big problem was that Einstein had replaced the one formula that describes gravity that Newton had with 10. So in order to what we call solve those equations, or in other words, find the curvature of space for any mass, and the curvature of space turns out to be what gravity is, you had to solve these 10 equations. And Einstein thought it was impossible. Schwarzschild went back,
But the interesting thing about him is that he did it immediately. We think of these things as taking, sort of percolating and the ideas there. But Schwarzschild took Einstein's equations and pretty much instantly worked out, not instantly, obviously, it was months of work, but he immediately saw the significance, and he was able to show that the theoretical existence of black holes from a standing start.
Yeah, I mean, he showed that obviously there is a valley of space-time around the sun, and the Earth actually goes around the upper reaches of that valley like a roulette ball in a roulette wheel. And he discovered that if you concentrate a mass more and more, that valley becomes steeper and steeper until it becomes a bottomless pit. Light cannot get out, and it becomes shut off from the universe. It becomes a black hole. And you're absolutely right. He did it within weeks. And then he wrote a letter to Einstein in Berlin, and Einstein was astonished to get this letter.
Astonished and horrified in a way as well.
Well, he never
believed
believed in black holes himself, because the big problem was he spent 10 years of his life struggling to get this theory of gravity. It was almost immediately Schwarzschild was showing there was a flaw, because if matter were to shrink under its own, become more concentrated and shrink under its own gravity, eventually it would become infinitely dense. This is called a singularity. It's a place where everything skyrockets to infinity. It tells you that your theory is wrong. It's broken. So this is why Einstein did not want to believe in black holes.
I want to come back to singularities in a bit, but before we do that, I want to talk about how black holes form, because, it starts off as a star. And I'm going to throw this open to you because obviously you know this better than me. And we're also going to need to, we're going to put supermassive black holes to one side, because a black hole that forms from a star is not going to be a supermassive black hole. It's going to be several times the size of the sun. But so what happens? Why does a star turn into a black hole?
Well, basically, because a star runs out of fuel. I mean, the stars are burning fuel, hydrogen fuel. They generate heat, and it's the outward pressure of that heat that stops gravity crushing the material.
Because gravity always won. Now, you did a book about gravity as well. That you did
yes,
the same
that's
thing for
right.
gravity that you
called
did.
The Ascent of Gravity.
For black holes.
Yeah, and so eventually, the fuel runs out, and gravity gets the upper hand and crushes the star. But if the star is particularly massive, there is no known force that can prevent that collapse down to a single point, a singularity. And that's what we get.
And so that's how you get a regular black hole. And how big is that going to be in terms of the amount of matter there is and the sheer size, I mean, the geographical size of it?
Black holes are very, very tiny. If the sun were to become a black hole, which would be pretty impossible, it would be about only 6 kilometers across. If you wanted to turn the Earth into a black hole, you'd have to squeeze it smaller than a peanut. So black holes are very, very small. They're very massive, but they're very, very tiny.
So in that sense, it's not a hole at all. It's an incredible concentration of matter.
As I say in the intro, well, it's not even a concentration of matter. The matter's gone. All that's left behind, the matter has gone somewhere. We don't know where, because our physics breaks down, so we don't know. But what's left behind is this region of warped space-time. And I think black holes are the simplest objects in the whole of science, because they're made of nothing but space and time. That's all that's left.
I see. Oh, so that brings me to one of my one of the things I didn't understand, which is that you have said, and other people have said, that when you get into a black hole, space and time, we know that space-time is a thing, but space and time, as it were, change places. They switch their vector or allegiance.
Well, yeah. So
what does that mean?
So, basically, what Einstein's theory of gravity predicts is that gravity slows time. Okay, and this is an effect which your mobile phone has to use in order to calculate your position relative to what we call global positioning satellites, because they've been moving in and out of the Earth's gravity, and so the clocks on board are slowing and speeding up. So this is an effect that affects your life. But near a black hole, this distortion becomes absolutely enormous. So if you were to fall into a black hole and you were to look back outwards, time would be flowing so slowly for you that you would be able to see the entire future history of the universe flash past your eyes in fast forward. As you cross the event horizon, the point of no return, as you just say, in a sense, space and time exchange places. That means that the actual centre of the black hole is in your future. So you can no more avoid the singularity than you can avoid tomorrow. That's why you cannot escape once you get inside the black hole.
You said that black holes are fantastically luminous, though. So if light can't escape a black hole, in what sense is it going to be luminous?
Well, this is the thing that people missed. They really did miss it. But actually, all matter is rotating in the universe. The Earth is rotating, our galaxies are rotating. So, of course, the matter that falls into a black hole swirls into the black hole rather like water going down a plug hole. And there's actually friction within that gas that heats it to millions of degrees. And so what we actually see is this accretion disk of material, which is glowing at millions of degrees. And we see it, for instance, in the most luminous objects in the universe, which are quasars. And these accretion disks, which are very tiny, are pumping out more than 100 times the light of an entire galaxy of stars.
So a quasar is a black hole with an accretion disk of material falling into it, is it?
Yeah, so what really surprised everybody was in 1963, Martin Schmidt, who was a Dutch-American astronomer at Caltech, which was where I was a student actually, discovered quasars. And these looked like stars, but he discovered that they were at tremendous different distances. And to be as bright as they were, really the energy of starlight was not enough. And so within about a year, people had guessed that the only possible source of their energy would be matter swirling down onto a black hole, but not a stellar mass black hole, a black hole of millions, maybe even tens of billions of times the mass of the sun.
Well, now there we come to that other question of the supermassive black hole. You've explained how we might get a black hole that was several times the mass of the sun, but we know now that there are these black holes at the centers of galaxies that are not only that are supermassive, that, as you say, can be tens of billions of times. That's not a star collapsing, is it? So where do they come from?
Well, that's a good question.
Okay.
Nobody knows.
We don't know.
Nobody knows. So initially, when quasars were discovered, we thought that these supermassive black holes with their accretion, blisteringly hot accretion disks, were powering the 1% of what we see as unruly galaxies. We see some galaxies that are clearly...
And what does that mean?
They have some kind of violent behavior. There's explosions happening in their cores, that kind of thing.
As opposed to like the Milky Way.
Quiescent. Yeah. So we thought initially they are powering these 1% of what we call active galaxies. Then, of course, the Hubble Space Telescope gets launched in the 1990s, initially with the telescopic equivalent of a squint, which cost $800 million to fix.
Again, you tell that story in the book because you're brilliant about bringing in sort of the human scale of these things. And that's an amazing story that Hubble was cocked up.
It was
and had to
one
be
of the biggest
corrected.
cock-ups in scientific history. Yeah, absolutely. Fortunately, it was possible to have one of the most complex space mission ever, to give it the effectively correcting lenses, so that it could actually see. And Hubble could look into the cores of nearby galaxies, and in every single one, it saw that the stars were whirling around so fast that they had to be in the gravitational kind of trapped by something really supermassive. So we then discovered there's a supermassive black hole in every galaxy.
So literally, you couldn't have a galaxy without a black hole. That sort of implies...
They are the missing ingredient. But for hundreds of years, astronomers have been trying to understand galaxies, and they've missed this ingredient that every one of them has a supermassive black hole in their core, including our own. And the reason that we only see 1% of the galaxies active is because in only 1% of the galaxies are they being fed. In the other 99%, they've run out of fuel, the gas and ripped apart stars, and so they're dormant. And so there's one in the centre of every galaxy. And you can ask me now, why is there one in the centre of every galaxy? And nobody has any idea. Not only that, but they don't know how they could possibly have got so big so quickly. So recently, NASA launched the James Webb Space Telescope, which is the successor of Hubble. And it's seeing galaxies very, very early on in the history of the universe, maybe when the universe is only a few % of its current age, and they've already got big black holes in their core. So it's a real mystery where they came
Already,
from.
because that's the. I mean, you could sort of imagine over billions of years, lots of little black holes coming together.
Well, that's one
But
possibility. There's not enough time.
That's
There's not
what
enough
we're seeing,
time.
though,
There's
is it,
not
when we
enough
look at
time.
these-
No, that is the problem. It's the problem of how they got so big so quickly is becoming more and more acute. So we don't know whether. Well, we don't even know what came first. Did supermassive black holes come first? Are they the seeds that the seeds of galaxies of stars? Around which galaxies of stars formed, or did galaxies of stars form first, and maybe a few stars became black holes and they merged and whatever, and something grew in the middle. So we don't even know that, but we do know that they play some crucial role in our universe being the way it is.
And indeed, that they regulate the birth of stars within.
Absolutely, and that's another real mystery.
How
because
does that work? How could that possibly be the case?
Well, this is one of the most surprising things which I write about in my book. I ought to tell you that these supermassive black holes are very tiny. So they are imagine a bacterium compared to London. So they're really, compared to their galaxy, they're like a bacterium compared to London. Mm-hmm. But we find that they've left an indelible print on the stars. So, for instance, in every one of these galaxies, the supermassive black hole is about 1/200th the mass of the what we call the bulge of
so
central stars.
0.5% of the whole mass of the galaxy, and yet appearing to have this enormous impact.
Absolutely. So their gravitational force is insignificant, and yet they keep this ratio of their mass compared to the mass of the stars. So there's an intimate connection in some way. Now, imagine a bacterium that could control the street plan of London. That's the kind of thing we're talking about. How can something so small have control its
And this is something else
galaxy?
we don't understand.
Well, I think as far as black holes are concerned, supermassive black holes, size does not matter. The important thing is the energy involved in their creation, right? If you walk past a house and a slate falls on your head, you know that what's called gravitational energy, the energy that slate had by virtue of being high up and now coming low down, has been converted into what we call kinetic energy, and it's giving you a headache. Okay, so when you form a supermassive black hole, you can imagine countless, God knows how many quadrillions of slates all coming together. The energy that is liberated, just like the energy that's liberated when a slate hits your head, is thousands of times more than the energy needed to blow a galaxy apart. So there's more than enough energy there for it to have some kind of imprint on the galaxy. But how that happens, we don't know.
We come back then to the Milky Way, which was, for various reasons, it wasn't the first black hole that was detected, but it was one of them, one of the early ones, and you go into detail how that, and it's just a stunning. I mean, there's some clever people out there, aren't there? It's a stunning story. We're not going to pursue that one because I want to ask you about the black hole, the supermassive black hole at the centre of the Milky Way is actually a bit of a tiddler compared with other galaxies. It's there's nothing to it, and that's probably quite important to us, is it?
Very important because it's 4.2 million times the mass of the Sun. And that makes it thousands of times smaller than the supermassive black holes in many galaxies. And in fact, the nearest big galaxy to us is Andromeda, and its supermassive black hole is about 50 times bigger than ours. So it's a real mystery why we're living in this galaxy with this tiddler. But it could be that we're having this conversation because that's the case. Because not only are black holes not black, but they don't appear like holes sucking in material. Very often we see jets of material coming out of their poles. They stab outwards in opposite directions for millions of light years.
And do we know why that happens?
We don't exactly know why that happens, but of course it's not just gravity that is involved. The accretion disk is a plasma. That means a charged gas. It has a magnetic field. We see that parts of the sun rotate at different rates, so the magnetic fields get twisted, and when they snap, material gets flies off into space, and we've seen that recently in the aurora when it hits the Earth's atmosphere. So something similar happens with these accretion disks in that the magnetic fields get twisted, and when they break, they catapult material in some way that we don't understand along these jets. And so this means they project these tiny little things, really tiny, project their power over very large distances, and they can snuff out star formation. So to answer your question, in the galaxies with the really big supermassive black holes, often early in their history, all the gas has been blown away by the supermassive black hole. This is the raw material of stars. So they ended up with one generation of stars, and then it basically star formation finished. We are living in a galaxy where we've had multiple generations of stars. Each generation has made more and more of the elements like carbon and oxygen that we need for life, for technology. So really, it's because we've got a very small supermassive black hole that has not blown away that raw material. There's been multiple generations of stars, and we're having this conversation.
One of the interesting things I found from your book is that I know that the nearest star to the sun is like 4 light years away, but close to the black hole, at the center of the galaxy, stars are much, much closer together. Like 2 light weeks distance between stars, which again is something that one hadn't visualized.
Well, I mean, I think I can't remember how many stars we can see with the naked eye, but it's probably
about 6,000.
6,000, yeah. But I mean, when you get near the centre of the galaxy, you're talking about millions or maybe even hundreds of millions. So if there was a planet, if we were on a planet near the centre of the galaxy, I mean, really, there'd be no night. The night sky would be completely papered with stars.
We have to come back to the singularity because regular listeners to Books podcast will know I've got a bee in my bonnet about this. I've always found the notion that infinity was an aspect of the material world, universe, difficult. I think it's a tool for mathematicians. And you describe the singularity as the stuff of physicists' nightmares. And there's another point where you say, given that the singularity predicted by Einstein's theory is not a real physical thing, the question is, what is the true endpoint of runaway gravitational collapse? So we're not really to believe that there is such a thing as a point of infinite density and presumably infinite heat or temperature.
No, it doesn't exist.
No.
So I mean, basically, the theory is telling us that it's been stretched beyond the point where it's applicable. An infinite thing is as you just pointed out, it's a mathematical entity. It's not a physical entity. We don't expect there to be anything.
You're a comfort to me, Marcus.
Yeah. So what it's telling us is that we need a better theory, really.
So it's the theory that's the problem.
Absolutely.
Then. Because I mean, we all sort of celebrate Einstein, and my goodness, he was he was a bit on the smart side, and his theory has been fantastically useful to us. But you're suggesting that perhaps we need a new theory to
Well, I mean, that's what's so interesting. He struggles to get this fantastic theory, which is past every observational test, but within it are the seeds of its own destruction. And he learns that, from a man serving on the Western Front within weeks of actually publishing his theory. So you can understand.
And of course, well, the
how he got a bit fed up.
Yeah. But he dealt quite well, did Einstein, with the way that science kept changing. He was always interested.
He never believed in black holes. But actually, the first evidence had been found in the 1930s by Karl Jansky, who was working for Bell Telephone Laboratories and was charged, he was only 25, 26, with discovering what radio interference there was for transatlantic broadcasts, and he discovered that there was this weird source coming from the Milky Way, and later there was a radio astronomer called Grota Reba who built this whopping great dish in his parents' backyard in New Jersey, and was the only radio astronomer in the world, and he discovered again there was something coming from the centre of the galaxy. But no one really, until the 1960s, had any suspicion that what we were seeing was supermassive black holes.
Yeah, this is the thing. The notion of a black hole depends on Einstein's theory of gravity. I mean, Schwarzschild would never have got there. If Einstein hadn't developed that theory of gravity, would black holes have been detected anyway? Would we have known? I mean, if they were detected, would we have been able to say what they were?
Well, I think it will have been detected. I mean, someone would have come up with a theory of gravity like him, but again, this is always the example of the physics that there was no real observational motivation for this. This was Einstein trying to find beautiful physics, and if it hadn't been for him, it might have taken another half a century before someone came up with it. But the person who discovered stellar black holes was Paul Murdin, who co-discovered them with Louise Webster.
And he was the origin of your interest. You saw
Origin
him
of my
speak.
interest, yeah. Yeah, so when I was
When you were 13,
12, my
12.
dad I was a member of the Junior Astronomical Society, and my dad took me to a meeting in London, and a man on with a walking stick kind of hobbled towards the lectern, and that was Paul Murdin. I didn't realise he'd had polio when he was a child. I learnt that recently. And he proceeded to describe Cygnus X1, which was the first black hole, and it blew my 12-year-old mind.
Why was that the first one detected and not the one at the centre of the Milky Way, which is a lot closer?
Well, I mean, strictly speaking, I suppose really 1963, 8 years before, we discover quasars, and we're pretty certain that it could only be a supermassive black hole that is powering them. But of course, always with these objects, we can never see them directly. We're inferring, so we're saying, well, what else could actually generate this amount of heat or light? What else could whirl stars around this fast? And it wasn't until relatively recently, 2015, that we discovered gravitational waves, which are, kind of oscillations of the fabric of space-time coming from the merger of black holes, and that was basically that was the proof that they existed. And then, of course, in 2019, we got our first ever image of a black hole, which was a 6.5 billion solar mass black hole in a nearby galaxy called M87. And, that was exactly what we expected, a void surrounded by glowing gas, which was falling in. So really, until, only very recently have we actually had direct evidence of their existence. It's always indirect.
And that direct evidence is two black holes merging, colliding with each other.
Well, because Einstein's theory does predict a unique signature for this. So I ought to say that this is a really important moment in the history of science, because we've always been able to see the universe, with our eyes and with telescopes since Galileo. But then in 2015, we got to hear the universe for the first time, because these ripples in the fabric of space-time are effectively sound waves.
You're extremely good in the book on the devices and the techniques that people use to investigate all these things. So I'm going to ask you in detail about LIGO, the let's see if I can remember what it stands for. The Laser Interferometric Gravity Wave Observatory.
Yeah.
Oh, I get a brownie point for that one. That one is the most astonishing machine, and it almost makes the Large Hadron Collider look like a Meccano set. Tell me about LIGO. How do they detect something as minute as a gravitational wave from a distant galaxy?
Well, it is incredible, because but basically they use a giant ruler, and when a gravitational wave...
How big is this ruler?
4 kilometre long ruler.
Okay.
So when a gravitational wave goes past, it kind of alternately stretches and squeezes that ruler. But I should tell you that it squeezes and stretches that ruler by far less than the diameter of an atom. In fact, far less than the nucleus at the centre of an atom. So it's
quite hard to measure then.
Very hard to measure, incredibly hard to measure, and that's why it took them four decades before they managed to do it. So it is an absolutely phenomenal, and that's why, of course, Nobel Prizes were awarded. One of which should have gone to Ronald Drever, who was a Scot in Glasgow, who had been one of the pioneers, but unfortunately got dementia and died a few months before the award.
So the LIGO is it's a ruler, but it's not a ruler made of wood or metal, is it? It's a ruler made of mirrors, or
it's a ruler made of light, of
light.
Laser light. So basically, you have a 4 kilometre evacuated tube. So you pump all the air out until it's better than like the vacuum of space, and you bounce a laser beam up and down this tunnel between suspended mirrors. So the mirrors they weigh, I think, about 43 kilograms, and they reflect most of the light on them. And you're looking for tiny variations. They're supported by fibres, which are like, I think about the width of a human hair, these 43 kilogram mirrors. And effectively, you've got the world's most sensitive seismometer. So the big problem that they had was not only detecting these tiny change in the separation of these mirrors, these separated by 4 kilometers, but was in actually screening out things like people riding past the LIGO site on a bike, or waves hitting the beach in California several thousand kilometers away, because all of these create signals of the same size as what they're looking for.
And the really interesting thing, one of the many interesting things is they detected their gravitational wave on the first test run. They thought it would be years before.
That is the really most extraordinary thing, because it was just what we call an engineering run, and they were just they were getting ready to use what we call advanced LIGO. And they weren't even ready to take any science, and suddenly this thing starts vibrating. The mirrors start vibrating, and far more than they expected. And even to this day, they've now detected about 100 of these events. This still is the most powerful event that they detected. So the first one was the most powerful. So then they spent many months, 6 months and more, trying to think, could this have been created by something else? I should tell you there are 2 of these rulers. One of them's in Louisiana, near Baton Rouge, and the other one's in Livingston in Washington
so they
State.
can compare their results.
Yeah, so
that bicycle going past.
Exactly. So they need exactly so, but then they had to rule out maybe someone at both sites slamming a door at the same time. All this kind of stuff. Then they had to think, well, could this be malicious? Could somebody have injected a malicious signal in? So there was actually a secret team whose job was to inject spoof signals into so to check that the scientists could tell the difference between a spoof signal and the real signal. And in fact, at one point, the scientists were on the verge of publishing when they were told, in fact, it was a spoof signal. So, but this one wasn't. This one was correct. And before they actually went public, they knew that they detected another one as well. And so they were pretty certain that that's what they'd found.
And so a gravitational wave is a movement in space-time. And do we only get them when 2 black holes merge? Is that the only circumstances in which...
The biggest problem we have is that gravity is very weak. I mean, you might think it's quite strong. You can leap...
When you fall out of a window.
Yeah, you might think it's quite strong. But actually, it's 10,000 billion times weaker than the force of electrical force holding the atoms together in your body. So it's fantastically weak. Because it's so weak, only the biggest masses with the most powerful gravity create gravitational waves that we could potentially detect. And I should tell you that this first one, I think they've been travelling for billion years or something.
Yeah, because you say that black hole collisions are only ever in the past. They're not happening now. Anyway.
Well, these are in distant galaxies, yeah.
Which by definition is in the past.
Yeah. And I mean, with the first one, to give you some idea, the power emitted in gravitational waves was 50 times more than the power emitted by all the stars in the universe combined. So had this thing not given out gravitational waves but shone with light, this single event would have shone 50 times brighter than the entire universe. It's the single most powerful event
quite a lot
ever witnessed by human beings. And again, why do we do this? We do it because we discover new things. Well, we're discovering that these objects that are merging are far bigger than any of the black holes that we predicted. As you said at the beginning of this interview, a star tends to leave a black hole of a few times the mass of the sun. We're seeing things, some of them are 100 times the mass of the sun. Very hard to understand where they've come from, unless we're seeing black holes that have already merged. So we're seeing a merger of 2 objects that were each formed in a previous merger. So these events are much more common than we thought.
One final question. And you've touched on some of it, but what are the highlights of what we don't know about black holes? What are the most important things? What do you hope we're going to find out in the future?
What are they doing? My whole book is subtitled How Black Holes Came In From the Cold. So initially they are thought to be so ridiculous as to not even be the preserve of science fiction. Gradually, over the last 100 years, they've moved more and more into the centre of physics until, I'm saying, well, I'm having this conversation with you because of the black hole.
One of the interesting things is you tell us that I think the first black hole was detected was in 1971. And by 1979, Disney are doing a movie called The Black Hole.
Yeah. I mean, a very important thing which we haven't mentioned was the coining of the term in 1967, because it's incredibly important to have this name that paints a visual picture. And of course, we now all talk about, I've lost my papers down a black hole or whatever. There's nobody on the planet who doesn't know the phrase black hole. And that was a guy called John Wheeler, who was the supervisor of a famous physicist called Richard Feynman. And it was a student who came up with that term. But it just shows you the importance of having
marketing, though, isn't it?
Yeah,
Because
it's
a great name.
Yes, it is. It is the great name, and we all have a picture in our minds of. We all think we have an idea of what black holes are. One thing I should just lastly say is that we talked about Paul Murdin, but I would really like to get Louise Webster the credit that she deserves. She was the co-discoverer of black holes.
She didn't get a Nobel Prize. And Jocelyn Bell, who discovered neutron stars, didn't get a Nobel Prize.
So the two endpoints...
Are we adding them to Rosalind Franklin of women who should have had it?
The two endpoints of the evolution of massive stars are black holes and what we call neutron stars. They are stars about the size of Mount Everest, but weigh as much as the sun. Both of which they're called relativistic stars because they can only be understood using Einstein's theory of gravity. Both were discovered by women. As you say, Jocelyn Bell, 3 Nobel Prizes for neutron stars. None have gone to her. And black holes, co-discovered by Louise Webster, who sadly died she had a liver transplant in Australia. She died of cancer at 49. Completely forgotten. Written out of the history of science.
This is an absolute travesty. Women are going to be up in arms.
It is a travesty. So I really hope that Louise Webster does get the credit that she finally deserves, really, for discovering black holes.
Well, one of the things that A Crack in Everything does is tell those human stories and bring those people to the fore. So, maybe you'll make a contribution to her being remembered. I found it an absolute page turner. I was just enraptured in every chapter. So thank you very much.
Well, thank you.
Well, the book is A Crack in Everything by Marcus Chown. It's published by Head of Zeus at £20. If you enjoyed this interview, please subscribe now on your favourite podcast player and we'll notify you of upcoming episodes. And Marcus, thank you very much. This was an absolutely fascinating time.
Oh, thank you for having me. I really enjoyed the interview. Thank you.
That was the Books Podcast, presented by Tim Hague. Email Tim on tim@bookspodcast.com, Twitter @bookspodcast, and Facebook @bookspodcasttim.